Kia ora Year 12 and 13. This is going to be the first of several videos on related rates of change, and this is part of Level 3 Calculus, the differentiation topic. It's one of the parts of the topic that students find the hardest, and also one of the parts that examiners like to use for excellence questions. So in this video I'm just going to do three very simple examples to give you the big idea, which is that this is all about using the chain rule. There'll also be a chocolate fish for the first person to find the musical interlude and tell me what the song is, but that's later on as an incentive to keep you watching, because this stuff is really exciting. Okay, on to the first example. Right, this is about a cube, and the cube is growing. Don't ask why, it just is. The side of a cube is increasing at a rate of 5 centimetres per second. We're going to underline that because that's really important, and that's a common pattern that we'll find in these questions. Find the rate of increase of its volume when the length of the side is 3 centimetres. So it's going to help us here to define a few things. We'll start by saying let the side length be x. And here's my cube. I'll draw another one. Oh, it's a bad looking cube, but there you go. So we've got the side length is x, and we're asked to find the rate of increase of its volume. So we're going to say let the volume be v. Now we know how to find the volume of a cube. V is equal to x cubed. So what I've done now is I've linked the v and the x. So let's go back and read what we've got again. The side of a cube is increasing at a rate of 5 centimetres per second. So we can write this as a derivative. The rate of change in the side length with respect to time is equal to 5. Right? And we can think of that as 5 centimetres per second, or some of you will be familiar with this notation. I think if you do physics you'll write it like that. Anyway, what we're being asked to find here is the rate of increase of its volume. So we are looking for dv by dt. Right, our goal is to figure out this thing here. So on the next slide we're going to look at how we can use the chain rule to solve this problem. When we started using the chain rule, we thought about it like this. We had an inner function and an outer function. Right, and we used the chain rule on problems like this. Y equals 2x plus 1 cubed. And we thought about the inner function as being 2x plus 1. So we can do the same thing here. How does our volume change with time? Well, the cube is growing, and so as the side length increases, the volume increases. And we know how the side length is increasing over time. So when we do problems about related rates of change, we're always going to use Leibniz notation, and it can help us to think about these quantities as fractions. Okay, it doesn't matter too much in the simple problems in this video, but it will be a good strategy later on. So now I just have to figure out these different bits. Well, we've got v equals x cubed, and we know dx by dt was equal to something. Let me just remember, I think it was 5. Just have to have a wee look back. Yep, so dx by dt was 5. So dv by dx is going to be 3x squared. So dv by dt is equal to 3x squared times 5. Right, now I just need to simplify that and then substitute in when the side length is 3 centimetres. So I'm going to pop in another slide to do that now. Okay, dv by dt is equal to 15x squared. And we want to evaluate that when the side length is 3. So that's going to be 15 times 9, and that equals 135. Now I need to be careful thinking about my units, because the volume of a cube is measured in cubic centimetres. So this answer of 135 means the volume is growing at 135 cubic centimetres per second. So just make sure that when you've got right through a problem like this, you always give the appropriate units, and you always need to check if it's a cubic centimetre, or if you're doing an area, a squared centimetre, and so on. So that's my first problem done. Okay, here comes the next one. Just make that easier to read. Alright, ink is dripping continuously onto tissue paper. An ink blot is forming. Maths is exciting. So here's my ink blot starting, and over time it's going to spread. And because we are being very precise, it's going to spread in a circular way. Okay, so don't go thinking about fancy psychology ink blots. It's just a dot that is forming a circle. So we can see that we're going to need to have something be the radius, so we'll let R be the radius of the blot, and we are being asked to figure out the rate at which the area is increasing. So let A equal the area. Now we know that A is equal to pi r squared, and we are trying to find dA by dt, so the rate at which the area is increasing. So using the chain rule, dA by dt will equal dA by dr times dr by dt. Now we know dr by dt, the radius of the blot is increasing at a rate of 0.2 millimeters per second. So dr by dt is equal to 0.2. Put the unit in. Right, so what's dA by dr? dA by dr is equal to 2 pi r. So on a new slide, I'll put those things together. Okay, so dA by dt is equal to dA by dr times dr by dt. Right, and dA by dr was, where did it go, 2 pi r times 0.2. So that equals 0.4 pi r. Now, the first question was, what is that rate when the radius is 7? Now notice that it's in millimetres, so that matches my units. So all we have to do here is substitute in r equals 7. So dA by dt is equal to 0.4 pi times 7, which is 2.8 pi millimetres per second. Okay, so it's okay to leave it like that. That's an exact answer. But for a more intuitive handle on that, it's 8.796 millimetres per second, and that is to 4 significant figures. So that's the first one done. Now the next question here takes a little bit more thought. Not much, but a little bit. So in part B, it's not clear at first what we've got to do, because we're being asked what is the rate at which the area is increasing after 3 seconds. Now we were told, well, we worked out that dA by dt was equal to 0.4 pi r. But we haven't been given a radius to substitute in directly. We've been given a time. So we need to figure out what will the radius be after 3 seconds. Now we know that the ink blot started, we can assume at time 0 there was no ink blot, and the rate of growth of the radius is 0.2 millimeters per second. So at t equals 3, r is equal to 0.6 millimeters. So that's what I've got to substitute in here. So after 3 seconds, dA by dt is equal to 0.4 pi times 0.6, which is 0.24 pi. Now I need to give my unit. My unit will be millimeters squared per second, or I'm going to give an approximate answer, 0.754 millimeters squared per second. And that's to, that's to 3 significant figures. Okay, the third question. Hopefully you're starting to get the hang of it. This is about a balloon. A spherical balloon is inflated at a rate of, should say 3 cubic centimeters per second. Sorry, that's a PowerPoint problem with the video package. Find the rate of increase of the radius when this radius is 2 centimeters. So a couple of things we need to know here. We need to know the formula for the volume of a sphere. I'll check, I think you get given this in the formula sheet, but it's one that you should know if you've done enough practice by November. And that's that the volume of a sphere is given by this. Also note that here I'm not looking for dV by dt, I'm looking for the rate of increase of the radius. Okay, so I'm looking for this. Right, now, here's the musical interlude. First person to email me and tell me the name of the song and the artist gets a chocolate fish. That's assuming that you go to Onslow. Apologies if you don't. Right, okay, I'm looking forward to getting some emails. So, we're going to write down what we know here. We draw a wee picture of a balloon. So there's the balloon. And we know that it's being inflated at this rate per second. So dV by dt is equal to 3 cubic centimeters per second. And we've got a relationship between the volume and the radius. So we can start writing down the chain rule. So dV by dt is equal to dV by dr times dr by dt. Right, the difference is this time we are going to be solving for dr by dt. So we're going to do that on the last slide. So dV by dt is equal to dV by dr times dr by dt. Now we got told dV by dt, so we can substitute that in straight away. Let's try and remember what it was. dV by dt was 3. Okay, so 3 is equal to, we had this, so dV by dr is 4 pi r squared. Right, so all I have to do is to solve for dr by dt. dr by dt is equal to 3 over 4 pi r squared. And I'm being asked to do that when r equals 2. So when r equals 2, dr by dt is equal to 3 over 4 pi times 2 squared, which equals 3 over 16 pi, and that will be centimetres per second. Right, notice that I'm working with the radius, so I'm back to just dealing with the base unit of centimetres. So 3 over 16 pi doesn't mean that much to me, so we're going to write that as an approximation. So let's work out what that is. Okay, so that's 0.059683 centimetres per second. Right, so that's the rate of increase of the radius when the radius is 2 centimetres. Okay, I hope that helped. From here we're going to do some harder ones where you have to look more carefully to find the link between the two variables. So that'll be coming up later on this week. Thanks for watching.